Namaste and welcome to the lecture on linear algebra through geometry. We have been looking at these subspaces associated with a matrix A, and the first the subspace that we saw was basically the null space of the matrix A, which corresponds to the solutions the solution to the homogeneous system of equations. So, basically you were trying to solve Ax equal to 0 and we collected the set of solutions x. These x are basically the n component vectors. We collected that x and we figured out that geometrically we figured out that this collection forms a subspace of Rn. I mean, if the matrix I mean if we had the matrix whose columns were linearly independent, we figured out that only the 0 vector gets mapped to the m component 0 vector. That means the 0 vector of the n dimension gets mapped to the 0 vector of the m dimension, and we said that null space was just the set containing the 0 vector from the n dimension. And then we moved on to figure out that okay, you can have a line passing through the origin, you can have plane passing through the origin, all these fellows were actually subspaces, and we figured out that our null space can be one of these. And subsequently we try to look at the set of vectors which can be expressed as linear combinations of the columns of the matrix A. So, when we are trying to say a set of vectors which can be expressed as linear combinations of columns of A, we were basically looking at I mean if you try to solve Ax equal to b, I want to figure out the set of all those b vectors which can be written as linear combinations of the columns of A. That means I want to write this as b is equal to x1 a1 plus x2 a2 plus xn an, where a1 a2 an are the n different columns of the matrix A, each of which is basically an m component vector. So, what we were looking for? We were looking for the set of b vectors which are basically m component vectors that can be expressed as linear combinations of the column vectors of the matrix A or the columns of the matrix A. And this collection, we figured out that this collection was a subspace of Rm, that means it was a subspace of the m dimensional vector space, and we gave a name for this. We said that the collections of all those b vectors which can be expressed as linear combinations of the columns of A is called the range of A or the column space of A. Now, let us try to look at the geometry of the column space of A for different matrices like what we did in the case of null space, and then move ahead with the other two fundamental subspaces associated with a matrix A, then go ahead with rank and nullity and other things, then look at other special subspaces that we have. Right. So, let us go ahead, let us look at the let us look at a couple of examples. So, let us take this example 1. Let us go back to our usual example, which is like say 2x1 plus x2. I will write this as b1 here because I am not looking at a specific b vector there. So, I will write this as b1 and b2. I will take this as x1 plus 2x2 is equal to b2. Now, what we want is we want to figure out what is the geometry of the column space of this particular matrix. So, what are we trying to look at? We want to look at the column space of A, column space of A where A is equal to this matrix which is 2 1 1 2. Now, what are we trying to do? We want to look at those set of vectors B which can be expressed as, let us say 2 1 1 2 into say x1 x2, which is essentially saying x1 into 2 1 plus x2 into 1 2. Right. Now, something interesting happens here. What is that? If you look at the two vectors 2 1 and 1 2, let us just look at the vectors 2 1 and 1 2, right. We know that these two are linearly independent vectors, right. These two are linearly independent vectors, and these two are two linearly independent vectors in R2, right. These two are two linearly independent vectors in R2. and from the module on the basis for a vector space we figured out that if you have a set of linearly independent vectors, the span of that set of vectors will basically form a vector space or a vector subspace. In this case, since this the two vectors that we have here, they are linearly independent vectors, we want to look at the span of these two vectors. We have already proved that, we have already seen in the previous lectures that 2 1 1 2 forms a basis for R2, right. When we looked at the basis for R2, we looked at 1 0 0 1, those two form the standard basis, and the other basis that we looked at was 2 1 and 1 2, they are linearly independent, therefore 2 1 and 1 2 form a basis for R2. If they form a basis for R2, then we know that every vector in R2 can be expressed as linear combinations of 2 1 and 1 2, right. If that is the case, now what we are looking for? We are looking for the set of all those B vectors which can be written as x1 into 2 1 plus x2 into 1 2, and we have already said this is a basis for R2. If these two vectors are the basis for R2, then the linear combination of these two vectors is going to give me the entire R2. Therefore, the set of B vectors which can be expressed as x1 into 2 1 plus x2 into 1 2 corresponds to, this basically is the entire R2. It is basically the entire R2, and therefore, and we know that R2 is a vector space. Therefore, we see that the column space of A, in this case column space of A in this case is basically entire R2, right. Now let us take a second example, our usual second example that we had, which basically was this example. We want to look at the column space of this matrix A, where A is equal to 2 2 1 1. You remember we had this matrix 2 1, 2 x1 plus x2 is equal to say something, and 2 x1 plus x2 is equal to say something else. So what we want to look at the set of all these B vectors which can be written as x1 into 2 2 plus x2 into 1 1, right. We want to look at the set of all these vectors x1 into 2 2 plus x2 into 1 1, and it is interesting that we see that 2 2 is actually a multiple of 1 1. So I am going to write this as 2 x1 into 1 1 plus x2 into 1 1, which is nothing but, I will write this as 2 x1 plus x2 into 1 1. That means the column space of this matrix A that we have here is basically the set of all those vectors which are multiples of this vector 1 1. So the column space is basically the column space of A in this case is the set of all those vectors which are this, I can write this as 2 x1 plus x2 is yet another scalar, let me call that as, let us say k into 1 1. Now what is this? The set of points that you have, this will be basically k into 1 1, the multiples of this vector 1 1 will actually be a line passing through the origin and the point 1 comma 1, right. And we already know that the whenever you have a line passing through the origin, that forms a subspace, and therefore in this case column space of A is basically line through the origin and passing through 1 comma 1. So the geometry here in this case is actually a line passing through the origin, and we found something interesting. A line passing through the origin is actually a one dimensional subspace of a high dimensional vector space. So what we are going to say is the column space of A is a one dimensional subspace of R2. Is that okay? And it is also interesting for this particular matrix that we took, where A, we found that the null space of A, what was the null space of A? Null space of A was also a one dimensional subspace of R2. That was also a line passing through the origin and passing through the point 1 comma minus 2, right. This is a line passing through origin, line through the origin and 1 comma minus 2. So, we just have this in mind, we will come back to this a bit later. So, the column space is a one dimensional subspace of R2, the null space is a one dimensional subspace of R2 in this case. Let us take another example, let us take our example in 3D. Let us take this example where I have x1, let us take this matrix A, let us take the matrix A, which is basically this 1 1 1, then we had this 1 minus 1 1, and we said this, okay, let us take this matrix 1 1 1, let us take this. If you look at this matrix, so I want to look at the set of all these B vectors which can be expressed as the linear combination of the columns of A. So, I want to look at x1 into 1 1 1 plus x2 into 1 minus 1 1 plus x3 into 1 1 1, this is what I have. Now, what we see here, the first vector and the third vector are the same. So, I will write this as, let us say x1 plus x3 into 1 1 1 plus x2 into 1 minus 1 1. Now, we see that again these two, this is basically sum of two scalars which results in another real number. So, let me call that as k. So, k into 1 1 1 plus x2 into 1 minus 1 1, right, this I will call this as k. Now, what is this? We see this 1 1 1 and 1 minus 1 1, these two are two linearly independent vectors in R3. We know that if there are two vectors in R3 which are linearly independent, then the vector space spanned by them is basically a two dimensional subspace of R3. Therefore, we are going to say the column space of A, is basically the span of these two vectors, span of this vector, let us say 1 1 1 comma 1 minus 1 1, which is basically, which is nothing but a plane passing through the origin, and defined by one 1 1 and 1 minus 1 1, that is a plane, and therefore, this column space of A in this case is going to be a two dimensional subspace of R3. So, here also we see that it is a plane passing through the origin and so on, right. Okay. Now, so what we see even geometrically, what we are able to see is that, look, the column space is going to be line through the origin, plane through the origin, right, you have the geometry which comes into picture. So, once we solve the system of equations, we will be able to check whether I mean what is the geometry and stuff. Remember, we had two questions when we looked at the, when we were about to define the column space, we had two questions. One, whenever you have Ax equal to b, you can find scalars x1 x2 xn such that Ax is equal to b, or there exists no scalar such that Ax is equal to b. These were the two conditions. We tried to solve for the condition where Ax was equal to b, that means you could find scalars such that Ax is equal to b. We have not addressed the case where Ax, there is no x, the case where you find no x such that Ax is equal to b. We will come to that a bit later when we try to do the least square solutions and stuff, right. So what the understanding from the previous lectures and all is that we have associated with the matrix A m by n, you have one subspace which is a subspace of Rn that corresponds to the null space of A, and one subspace which is basically a subspace of Rm which corresponds to the column space of the matrix A. Now whenever you talk of matrix A, you also have the other matrix which is basically the A transpose which is there. So what we do is we start focusing on A transpose now, right. So similar to how we have null space associated with the matrix A, we can associate null space with A transpose. That means you can find set of vectors such that A transpose y is equal to the 0 vector, but the only thing is the y vector that we are going to have is going to be an m component vector, because A transpose is an m by n by m matrix. Therefore A n, let us look at this. So now consider A transpose. A transpose of a matrix A m by n. Now what we see? We see that A transpose is basically an element of R n by m. That means A transpose now operates on, or it transforms m component vector to give n component vector which is C n cross 1. Is that right? So A transpose is basically this. Now what we have is, we can again associate a null space with A transpose and a column space with A transpose, right. So what we have is, we are going to look at null space of A transpose, which we call it N A transpose, or which is the null space of A transpose. So what is this? This is basically the set of solutions, say y in Rm such that A transpose y is equal to 0 n by 1. That means you are trying to get all those vectors y, m component vectors y, which gets transformed to the, or which gets mapped to the 0 vector in the n dimension. So you are basically looking for all those m dimensional vectors which get mapped to the n dimensional 0 vector by the action of A transpose. Is that clear? So that is what we are going to look at, and that is what we call as null space of A transpose, and what we note here is null space of A transpose is a subspace of Rm. Right, it is a subspace of Rm. Similar to this null space of A similar to how we had the column space of A, now I can talk about the column space of A transpose, right. So let us look at this. So what are we going to look at? We are going to look at the set of all C vectors, set of all C vectors which are element of Rn, which can be expressed as linear combinations of columns of A transpose, right. So what are we going to say? We are going to say this C which is basically n component vector. This we are going to look at this as, let us say, some alpha 1 A. You see, the columns of A are precisely the, I mean the columns of A transpose are precisely the rows of A, right. The columns, we know how to get the A transpose. A transpose is nothing but the matrix whose columns are the rows of A. So I am going to write this as A1 transpose, or the first column of A transpose, that corresponds to the first row of the matrix A, plus alpha 2 A2 transpose plus etc. plus alpha m in this case, because you are going to have, you had m rows and n columns for A transpose will now become n rows and m columns, right. So I am going to have alpha m A m transpose, right. Now this is basically the set of all those C vectors. C vectors are in Rn. So this is going to be the set of all linear combinations, set of all those vectors which can be expressed as linear combinations of the columns of A transpose. We are going to call that as the column space of, this is called column space of A transpose. It is also called as the range of A transpose, and it is also the row space of A, because the columns of A transpose is precisely they are precisely the rows of the matrix A. So we are going to call this as row space of A. So what do we have now? We have Rn. On the Rn side we have two subspaces of the matrix given A m cross n, given A element of R m by n, that is an m by n matrix. On the Rn side we have a null space of A which we call as NA, and B we have column space of A transpose, which is, let us say, range of A transpose. Let me write that as R A transpose, right. The notation is R A transpose, or we can say this call space of A transpose, which also corresponds to the row space of A transpose, right. On the Rm side, what is it that we have? Excuse me. So on the Rm side, what do we have? A, we have null space of A transpose, and B we are going to have column space of A, which is also called as the range of A, right. This is what we have. So the four fundamental subspaces that are associated with any given matrix, any matrix A, are the following: the null space of A, which is a subspace of Rn, the column space of A transpose, which is again a subspace of Rn, the null space of A transpose, which is a subspace of Rm, and the column space of A, or the range of A, which is the subspace of Rm. So these are the four fundamental subspaces. Given a matrix, we have all these four subspaces associated with the matrix, right. Okay. Now before we end the lecture, let us look at a little bit more. Let us just give look at the dimension of each of these subspaces, right. Let us look at the dimension of each of these subspaces. Let us first of all look at, let us define this. So null space of A, null space of A, the dimension of null space of A remember any vector subspace has basis and the number of elements in the basis is going to be called as the dimension of the subspace. So, the dimension of the subspace null space of A is called nullity. Dimension of null space of A is called nullity of A. Okay. And typical notations are it is lowercase n comma a nu comma a. So, this is the nullity. So, the if you consider null space of A, the dimension of null space of A is basically called the nullity of A. So, that is the definition for nullity. If the null space of A is the null space of A is, let us take some cases A, only the trivial subspace of Rn, that means it is just the 0 vector in Rn, then nullity of A is basically 0, which means this implies the null space is a 0 dimensional subspace. This implies null space is a 0 dimensional subspace of Rn. The next one is basically this, a line passing through the origin. If the null space is a line passing through the origin, then the nullity is 1. The nullity is 1, that means mu A is equal to 1. See if the null space is basically a plane passing through the origin, a plane passing through the origin, then the nullity is 2. Yeah. Now, let us look at the dimension of the column space of the matrix A. So, we are going to look at the dimension of the column space of A. Column space of A, this is something which is interesting in the sense this is called the rank of the matrix A. This is called the rank of the matrix A. Denoted as lowercase r A, or we are going to say rho A, right. This is basically the rank. Now, if you look at the dimension of the column space of A, that basically corresponds to the number of elements in the basis for the column space of A. Now, if you want to look at the basis for the column space of A, you can look at the columns which are linearly independent in the matrix A. the column vectors which are linearly independent in the matrix A. Now the moment you find the linearly independent columns in the matrix A, those linearly independent vectors can actually be the basis for the column space of A, which means the number of linearly independent columns in a matrix corresponds to the rank of the matrix A. So let us write this: the number of linearly independent columns of A is called the rank of A. And something more, what is that? The number of linearly independent columns, if you see, whenever you have your dependent columns, or let us say dependent columns, and when you try to do the row reduced echelon form, right, when you try to do the row reduced echelon form, we also get the idea of pivot variables, and we also have this pivot variables and free variables, right. And when we looked at this row reduced echelon form, we said that the number of pivot variables in the row reduced echelon form of the matrix A corresponds to the rank of the matrix A, and the number of free variables that we have, if you look at it, the number of free variables in the row reduced echelon form of A corresponds to the nullity of A, right. So here we are going to write this one. What is this? This is also the same as the number of, these are the various definitions for rank, the number of pivot variables, the number of pivot variables in the row reduced echelon form of the matrix A. Right, and nullity, we are going to say the number of free variables, in the RREF of A, in the row reduced echelon form of A, is equal to nullity of A. Right. More to it, this number of free variables, we also define the rank in the case of row reduced echelon form as something else. This is equal to number of non-zero rows in the row reduced echelon form of A. That is also called as the rank of A. So what do we do here in case of this? This is also equal to number of 0 rows in RREF of A, in the row reduced echelon form of A. Now let us make one more interesting comment, and we will look at some interesting result here. Suppose I have this row reduced echelon form of A, right. So let R of A be the row reduced echelon form of A. Now we know that there are a few columns which will be pivot columns, there are a few columns which will not have pivot elements at all, that will be attributed to your free variables. So we know that the number of pivot variables in A, in RREF of A, in R of that is exactly what I have written as R of A plus the number of free variables, in RREF of A is equal to number of columns in A, right. You cannot go beyond the number of columns, you will have some columns which will have pivot elements and some columns which will have free variables. If you add the two together you will get the number of columns of A, right. That is exactly what we are going to put it in a different form, we are going to call that as the rank nullity theorem. Rank nullity theorem. What it says is rank of A plus nullity of A is equal to number of columns of A. Right, rank of A plus nullity of A is equal to number of columns of A, which is exactly what we saw here. Rank of A was basically the number of pivot variables plus nullity of A is basically the number of free variables, both of them in RREF in the row reduced echelon form of A corresponds to number of columns of A. Right. So, this is a very important result in linear algebra where it says the rank of A, the dimension of the column space plus the dimension of the null space of A is equal to the number of columns of A. The dimension of the null space of A, the dimension of the column space of A plus the dimension of the null space of A is equal to number of columns of A. There is a nice catch here, what is that? The dimension of the column space of A, you call that as a rank. The column space of A is basically a subspace of Rm. The null space is a subspace of Rn, and what we say is the dimension of the vector space or the subspace in Rm plus the dimension of the subspace in Rn is equal to the number of columns. That is what we are going to see, I mean that is what it means, and we will see in, probably in the next couple of lectures we will see that the dimension of the null space of A plus the dimension of the column space of A transpose. Remember, column space of A transpose was also a subspace of Rn. So, the dimension of a null space of A plus the dimension of the column space of A transpose is equal to the dimension of Rn, which is equal to n. So, what does it say? Nullity of A plus the rank of A transpose is equal to number of columns, I mean is equal to Rn, and it also says rank plus nullity of A, rank of A plus nullity of A is also equal to n. Essentially we will see that the row rank of the rank of A and the rank of A transpose are the same, and that is what it boils down to. So, what we will do is we will just dwell upon that in the next couple of lectures, where I am going to introduce the idea of orthogonal complement subspaces. We will look at the idea of orthogonal complement subspaces, and then we will see that if you have a vector space and you can find two subspaces which are orthogonal to each other, then the sum of these two dimensions will be equal to the dimension of the original vector space to which these fellows are subspace of. And in that context we will also prove that the null space of A is orthogonal to the range the column space of A transpose, and null space of A transpose is orthogonal to the range of A or the column space of A. So, we will have all these results, and these are the things that we will be focusing on in the next lecture, and after that we will look at the idea of eigenspaces. So, orthogonal complement subspace. We have seen the 4 fundamental subspaces here, which are basically the 2 null spaces and the 2 column spaces. These are associated with every matrix, and now what we do is in the vector space we will be introducing the operation called the inner product. Once you define the inner product operation, we call that vector space to be an inner product vector space, and through that we will define orthogonal complement vector spaces. So that is yet another vector space that you can, I mean you can look at orthogonal complement vector spaces, which is basically what we just discussed some time back. And we will look at square matrices, wherein which we will look at the set of eigenvectors associated with a particular eigenvalue. That will be yet another subspace or a vector space, but that is not available for all the matrix. I mean not all the matrices will have the luxury of having the eigenspaces, because for a rectangular matrix eigenvalues and eigenvectors are not even defined, because the determinant of rectangular matrix is not defined and so on. Therefore we will look at only square matrices, which means these, apart from these 4 fundamental subspaces, you can associate certain other subspaces which may not be there for all the vectors, all the matrices, but we are going to look at this eigenspace which is associated with your square matrix. So that will be the agenda for the next couple of classes. Namaste.